Welcome back, everyone. Up until now, the focus of our journey together has been solving problems using integrals. So we've been interested in understanding what an integral really was, so we could break things up into pieces and add up the pieces and get an answer to some sort of real world problem. Now all that changes. Now we're not really interested in just setting up an integral to solve some problem. We are going to hear about where these integrals came from at all. We're going to be interested in how we actually evaluate them. And there's several different tricks or techniques, maybe a better sounding word, to evaluate these integrals. That's what the next section of material is all about, how we actually compute these integrals. Now, it might be worth taking 10 seconds of your time to remind everyone why such a thing might be important. Because when we look at things like these integral sheets and derivative sheets that we passed out at the beginning of the semester and said, here are the things you must have memorized, and now I tell you today that that time has come. It looks awful and scary and a long list of stuff, and it's not unreasonable to ask, why do we have to bother to do this? Especially, why do we have to bother to do this without a calculator? And the answer is pretty much the same reason that you had to learn your multiplication tables, at least more or less, you know, even though a calculator will multiply for you. In other words, it's really sort of silly to say, oh, I don't have to know what 2 times 3 is because, if I ever needed to know what 2 times 3 was, I could grab my calculator. But you need to know what 2 times 3 is so often that it's one of those things that you ought to have memorized. Now, there's probably some multiplication facts like, was it 54 and what is that, 7 times 8 or whatever the 54 and the 56 is. I always have to stop and think about those. So we're not talking about that. It's not that we're going to try to memorize every possible way you could do an integral, but you have to know the basics because these will happen so often in later classes that it will be like your multiplication tables are. That if you have to stop and think about it or grab a calculator to be able to do one of these integrals, that you're going to get completely lost as a goose. So that's the real reason for this next set of material. And again, at times it's going to seem a little frustrating, and it's also going to be tempting in the homework to grab a calculator and punch in an answer, and or Wolfram Alpha or some such something, and say, "Oh, look, I can do all this, with WebWork homework by punching into the calculator." And there are times when you can. If all WebWork is doing is checking the answer, you know, that's not legal, but it would work. The homework that you have to upload is a little different, and you'll have to work out things and show your work, and that's one reason why that set of homework counts more. Of course, if you fall in the habit of using your calculator to do all the homework, then on the exam, of course, you won't have your calculator. It will be unpleasant. So what you want to do is practice as much as possible doing the homework as though it were exam time. And again, so why do we bother with all this? It's because these are such foundational ideas that you're going to see them again in later classes, especially things like differential equations or other physics and engineering classes. And this will be expected to be something that everybody knows. And one of the biggest complaints that in the math department we hear from engineering and physics is you graduate all these people from calculus and they don't know what's essentially the next several lectures we're going to be talking about. And well, we're going to try to fix that because we're going to test you over it. And hopefully by the time you're done, you'll know this stuff. This is not just something to learn and forget. This is the multiplication tables of the rest of your life of math. So hopefully that explains why we're interested in doing this stuff. Now, the sheets that you've had, hopefully you've had a chance to be looking over them, to have most of this floating around in your head. It's may be helpful to take a few minutes and point out some of the things you might not have noticed on the derivative and integral rules, because this is all, of course, Calculus 1 material, except for those very last two formulas, the number 13 on the derivative sheet and 14 on the integral sheet, those very last ones that have SINH and COSH. Those are not Calculus 1 formulas. Those are hyperbolic trigonometric functions, and those will appear in Cal 2 in a few more lectures. So those last formula on each page you don't have to worry about, but at least for now. But The rest of it is all Calculus 1 stuff that you should have seen in Calculus 1 and may or may not remember because um, it's completely understandable when you're rushed at the end of Calculus 1 trying to get through um, integration. Some of this stuff gets lost in the shuffle of finals and stuff because it happens at the very end. A couple of quick things to point out on the derivative side. I mean, a lot of those rules are really simple, like the derivative of e to the x is e to the x and so forth. One rule that you may not have thought about before, the derivative of square root of x, number 2 on the derivative sheet, is 1 over 2 square root of x. Okay, what? That looks weird. But if you think about it for a second, it is just the normal power rule. So you treat the square root of x as x to the 1/2 power. When you take the derivative, you bring down the 1/2 power. That's where the 1/2 comes from. And then you get x to the, well, negative 1/2 power. So why did I write it as a square root in the denominator? Well, of course, that's what x to the negative 1/2 power is. The negative moves it down to the denominator. The 1/2 makes it a square root. So why write the derivative of square root of x as 1 over 2 square root of x? Because if you see a square root of x in the denominator, that's a hint that it might have been the derivative of another square root somewhere in the problem. So later when we start doing integration by substitution, when you see a square root in the denominator, that tips you off that that may be another square root's derivative, something that you can use with substitution. A few other things to point out. Maybe you haven't noticed the pattern for derivatives of the trig functions. So if you notice the trig functions on the left, sine, tangent, and secant, right, have their matching cofunctions, cosine, cotangent, cosecant. And if you look at the pattern for a second, it may be written this way, it's easy to pick out that the derivatives of the cofunctions are all negative. They're just negative versions of the non-cofunctions. So the derivative of cotangent is negative cosecant squared instead of derivative of tangent, which was just secant squared. So all the cofunctions get minus signs and they just get switched around in code, right? So derivative of secant, instead of being secant tangent, derivative of cosecant becomes negative cosecant cotangent. One other pattern that you may not have ever noticed, I hadn't until my first PhD student who had been teaching at the Air Force Academy pointed this out to me. He said, "Oh yeah, this is how we teach at the Air Force Academy. We tell them to remember supersonic transport," which maybe that makes more sense at the Air Force Academy, but it's SST. And the point of this mnemonic was you have two S's and a T. That's the way the derivatives of tangent and secant work. So I always had a hard time remembering whether the derivative of tangent was supposed to be secant squared or whether it was supposed to be secant tangent, right? In other words, getting the derivatives of secant and tangent mixed up. And here's how you remember. There's always two S's and a T. So the derivative of a tangent, well, you already have a T. So that's why the derivative is secant squared, because you need two S's. The derivative of secant, we only have one S, so you need another S and a T. So that's why the derivative is secant tangent. So hopefully that helps. That helped me because it made it easier for me to remember that part. Maybe you have your own mnemonic for remembering things like this, but those are sort of the basic facts that we'll of course have to have memorized. A little further along are the inverse trig functions, and again notice that the cofunctions all have negative signs that show up, right? Again, I almost like to imagine this as like the co is like a little box that they carry around their neck, and when the derivative comes up to it and whacks it, sort of like Thor with his hammer or something, or maybe it's an axe now with Stormbreaker since Infinity War. Anyway, when the cofunction gets whacked with the derivative, it breaks open the little box and the minus sign falls out. So all the cofunctions are their inverse cofunctions have a minus sign that the normal functions in there don't have, an opposite sign at least. The inverse sine, inverse tangent, inverse secant functions are all there. Those are important to memorize and to have in the back of your head. When we start doing trigonometric substitution, knowing what these derivatives of the inverse trig functions are will help you know which substitution we want to make. So from the integral side of the sheet, maybe these are a little less well known. These sometimes get brushed over a little bit in Calculus 1. I mean, not number 5, right? Because the derivative of sine and cosine are well known, so the integrals, of course, are well known. But the integral for tangent and secant, And of course, notice the integral for cotangent and cosecant, we don't really have to worry so much about because if we know the first ones, we know those. They just get minus signs and they get code, right? The integral for tangent is log of absolute value of secant. And the integral of secant is log of absolute value of secant plus tangent. So that's not quite as obvious, but that same sort of pattern we saw before with the derivative of a tangent being a secant squared, well, derivative of tangent just had a secant in it. So you get log of absolute value of secant. Whereas the derivative of secant had a secant tangent. So the integral kind of almost sort of follows that pattern in that it's log of absolute value of secant plus tangent. So those aren't obvious, but those are incredibly important. Number 6 and number 7 we will use a lot when we get to the section on trigonometric substitution. And if you don't know those, then you just miss those questions because there's no way to do those questions without having, especially number 6 and 7 on the integral sheet, memorized absolutely cold. Maybe the other most important formulas to know off the integral sheet are the ones for inverse tangent. So the derivative of inverse tangent was 1 over 1 plus x squared. So of course the integral works the other way. But number 12, you may not have seen before or have thought about, but we will use it constantly, especially in the section on partial fractions. So if you have 1 over a squared plus x squared, then you get, as its integral, without having to do any extra work or trying to manipulate anything, we'll just know this is the formula, that you get 1 over a, then inverse tangent of x over a. The reason for this is you could factor that a squared out of the denominator and do integration by substitution and use the old formula for inverse tangent to get this one. But that's so important that we'll want to be able to just do it. So if you're given like 1 over 9 plus x squared, well 9 is 3 squared. So you get 1/3 inverse tangent of x over 3. So that's the sort of stuff that we'll need to do quickly enough that we'll just have to know it. So speaking of integration by substitution, that is usually the last thing that we cover in Calculus 1. And sometimes it gets shortchanged a bit because it happens at the very end of Calculus 1. And everybody's so frantically trying to get ready for the final that they sometimes don't appreciate how substitution works. But not only do we have to know substitution really, really, really well, we really need to know it better than we usually teach it in Cal 1. In other words, we have to be able to do substitution so quickly that it's almost second nature. So here's an example. I'm going to work this kind of the slow way, the way that you probably saw it in Calculus 1. So what we have is not cosine of x when we have a formula for that. Right? We have cosine of 2x. So you can sort of imagine this as cosine of some stuff. Okay? What's really going on here is, derivatives are integrals, indefinite integrals are derivatives backwards in some sense. They're anti-derivatives. So integration by substitution is kind of the inverse operation to the chain rule. So instead of taking the derivative of cosine of a bunch of stuff, we're integrating cosine of a bunch of stuff. And thinking of it as a bunch of stuff maybe helps a little bit, because I'm going to let u equal that stuff. Now, that's easy enough. We can replace the green stuff, the 2x, with a u. So in just a second, I'll have a cosine of u, which looks good because that's cosine of just one variable, and I know how to integrate that. But there's still that dx floating around I have to deal with. So to turn the dx into a du, well, I'll just take the derivative. So if u is equal to 2x, then the derivative du would be 2 dx's, right? And now this is the way I would write this if I were doing Calculus 1. I would say, here, take and add in a 2 next to that dx. So then what I can do is replace the brown 2 and the dx with the red du, and I'm good to go. And I can turn the cosine of the 2x into a cosine of u, and we're set. But if I put the 2, that brown 2 there next to the dx, I have changed the problem. The only way to keep from changing the problem is to undo my multiplication by 2, which means I need to stick a half outside, because you can always slide a constant in and out of the integral sign. So by putting a 2 on the inside and a half on the outside, they would cancel each other and get me back to what I started with. So I haven't changed the problem. But I don't want to do that. I want to leave the 2 with the dx, turn the 2 dx into a du, then take the 2x inside the cosine, turn that into a u. So I end up with a 1/2 on the outside, then the integral of a cosine of u du. And now that's an integral with just one variable, so I know what the integral of cosine of u is. It's sine of u. Now substitute the 2x back in there for the u. And don't forget the plus c, right? Well, on almost all these problems we're going to be doing, they're indefinite integrals, so they'll always have the plus c at the end. Now, here's the problem with what we just did. That took too long, okay? We need to be able to do this in like 5 to 6 seconds, because this kind of problem is going to show up maybe 6, 7 times in a problem, say from the next lecture. We might have to do this kind of integral several times just in one problem. And it won't be the main point of the problem. This is just a sort of sideline. It's sort of like when you're working some sort of problem and you have to multiply two numbers together. I mean, you have to be able to do it very quickly, and that's not even the main point of the problem, right? That's what's happening here. So here's maybe a quicker way to understand what's going on. Just like when we did the chain rule, we would take cosine of, say, some stuff, and the derivative would become negative sine of the stuff, and I'd multiply by the derivative of the stuff. That's the way I always explain the chain rule, right? This is the chain rule backwards. So I had cosine of some stuff, so when I integrate it, I get sine of the same stuff. Stuff doesn't change. But instead of multiplying by an extra 2 on the outside, I divide by it. And so that's the easy way to think about this. And we're going to need to do this so often that you're going to need to be able to do this kind of thing really, really quickly. Right? So again, let me say that one more time. You have cosine of some stuff. So when you integrate that, you can make that sine of some stuff and just divide by the derivative of the stuff. So long as, of course, in this case, the stuff was just a 2x, so that when I can divide by a half. If I catch myself having to divide by like 1 over 2x cubed or something, that doesn't work, right? So I can't have an extra x floating around that I invent. In other words, I could stick in a brown 2 and a brown 1/2. I can't stick in a brown x. Here's another example. Well, what do we do with this, right? This is actually kind of a tricky one, because your first guess is to think that maybe I let that whole denominator be my u. Right? If I let the whole denominator be my u, then maybe I could get a 1 over u, which I can integrate and get a log, and we're good to go. But what's the derivative of all that stuff on the bottom? The 1 plus 4t to the fourth. Well, the derivative of all this stuff on the bottom would be 0 plus 16t cubed, right? So I would need if not 16t cubed, I'd at least need some kind of t cubed in order to make the substitution work. Well, I've only got a t, not a t cubed. So darn, that just doesn't work. I don't have enough t's to make that work. If I let u equal the whole denominator, the only way I can make substitution work is if I had a t cubed, and I don't. So what do we do? Well, if we stare at it a little bit and think about our derivative rules, there is another rule that looks like it might work here. Not 1 over u, but maybe 1 over 1 plus u squared. In fact, if we do a little bit of algebra, I could take that 4t to the fourth and make it 2t squared, all in parentheses, squared. You see that that's obviously the same, because 2 squared is 4 and t squared squared is t to the fourth. So what I really have is something that looks like an inverse tangent setup. 1 plus some green stuff squared. Now, what's the derivative of my stuff, right? The 2t squared. Oh, that's easy. That's 4t. And sure enough, I have the right extra variable. I have a t sitting there. So what I'll need to do is put in a 4 and put a fourth on the outside, and we're good to go. But again, I need to be able to do this really quickly, so I'm just going to say it, right? I put in a 4 next to my t, put a fourth on the outside. This gives me 1 over 1 plus u squared, which gives me an inverse tangent, and there we go, 1/4 inverse tangent of 2t squared plus c. Now, I did that really quick, and the point is you'll have to do this really quick too. So if you're a little fuzzy on this, of course, there's a lot of examples in the homework to give you practice on. And if you have questions, email me and I'll be happy to go through any of this and make sure that you're okay with how all this stuff works. But these are problems that have to become just absolutely second nature. So, if you can't do a problem um, like these very, very, very quickly, you're going to be in real trouble when we get to the hard stuff. So make sure that you memorize the trig formulas. Obviously, the derivative and the integral formulas, we have to know those absolutely cold. And then we have to be able to do substitution really fast because that'll be a very small part of a much bigger problem to come.